So we've looked at the idea of what happens when you have a solution, and we learned the terms with that. But what happens when those particles are just a little bit larger, where they're not a true solution, but it's still really small? So that's what this next part is going to be about. So here we have a couple of new terms: colloids, emulsions, and suspensions. Now, this colloids and emulsions are whenever the particles are still too small to be filtered out. So if you use filter paper, this is going to pass right through. But they're larger than the components of a solution in that they can scatter light. And that's going to become important here in a couple of slides. Now, colloid is a stable dispersion of fine particles of one substance in another. So it looks the same top to bottom. You can't tell that there's particles there just by looking. They're still too small for that, but we'll get to that one. So like it says, they're larger than solute particles, but they can scatter light. So examples of colloids include soap and water. And if you take a few drops of milk and put it in water, that's also a colloid. Now, an emulsion is a colloid where the microparticles of one polarity are suspended in the liquids of another polarity. So let me give you an example. So let's think of milk. Now, if you've ever had fresh milk from a cow or a goat, or actually a person, breast milk does the same thing, it's actually going to separate into layers. And so you'll get the milk, and then you get like a cream, and the really fatty stuff goes to the top. But when you go to the store to buy a gallon of milk, you don't want it to separate into layers. So what they do is they add what's called an emulsifying agent, and it's going to surround the fat molecules for milk, or it just depends on what your emulsion is, and it keeps them suspended so that they don't separate out. So homogenized milk is an example, mayonnaise, hand cream, lotions, they all use some sort of an emulsifier, and they use polarity to help them. So on this, we also look at the idea of hydrophilic and hydrophobic. Hydrophilic means it's something that's water loving. These are usually polar substances that have charges, so water is going to be attracted to that part of the molecule. And then they'll have another part of the molecule that's hydrophobic, meaning water fearing or water hating. These are usually like a long hydrocarbon tail that are nonpolar, that they don't really like water, but they like the grease and the fat and the oil. So that part will surround that portion of your substance. And with that, they can actually keep it suspended in your substance, in your colloid. So again, not a true solution because the particles are too large, and we have to use something to help them mix up. And I will show you a picture of this on the next slide. Now, a suspension, the particles are going to be a little bit larger here. So here we actually get to the point where they can sometimes start being filtered out. So this is usually some sort of a dispersion of solid particles that will settle out over time. So when we can start to see some different layers, milk of magnesia, calamine lotion, Pepto-Bismol, those are all going to be examples of suspensions. I think I also have another picture for you on the next slide. So here's an example of an emulsion. And so here they're making salad dressing. Well, you know, normally when you make salad dressing, there's some sort of oil and there's some sort of water, but water and oil don't like to mix. So normally they'll separate out. Well, again, you don't want that to happen. So before you serve it, you have to shake it really good, but maybe you don't want it to, again, separate out so easily. So you add an emulsifier. The one they're adding here is lecithin, which is a component in egg yolk, and there's also a soy component that you can use. And what it's going to do is when you mix it, here's the particle here in the very center. It's got this great big molecule, and it has one end of the molecule has charges. So that part really, really likes water. We call that hydrophilic. And then the other part is this long hydrocarbon chain. It actually has two long hydrocarbon chains, and that's hydrophobic. It likes the oil. So what'll happen is that hydrophobic part will surround an oil droplet. It's trying to show that down here. It's the little things that look like little matchsticks sticking up in there. And then it'll stick that hydrophilic end out the side, and so that part's attracted to water, and so it'll stay suspended. But then the oil droplets don't come in contact with one another because there's some charges on it. And so two separate molecules surrounded by your emulsifier have enough charges that they try to stay separated from one another. So that's why it'll stay suspended. Now over on the right we have a sample of blood, and it's showing how it given time, or here they've centrifuged it, which that just means you put it into a little machine and it spins it super fast, and that causes the solids to go ahead and separate out. So we see the red blood cells at the bottom, and then the top is going to be all of your good old serum. Now, because we can't actually see the size of the particles, because that's ultimately what determines the difference between a solution and a colloid, there is a way that we can experimentally, get an idea if they're really small or just really small. We can see if they're big enough to scatter light. And to do that, we use something called the Tyndall effect. So the Tyndall effect goes through the idea that light is scattered in a colloid, but it passes through a solution. So we have this picture, it has these little cuvettes, and there's a laser light that's being sent through. And you'll see that that light beam is going to go ahead and it's going to have some interaction with the glass, but then it's like it disappears. Well, that's because as it's traveling through, the solution particles are so tiny that they don't affect that light beam. Now, when it goes through the second cuvette, notice you can see a faint red line through there. Well, that one's dealing with the idea that as it's going through, this is our colloid or our colloidal dispersion. It's kind of fun to say, colloidal dispersion. It starts to interact with those particles, and so you get a scattering of the light. So you can actually see the light beam as it's traveling through. Now, you may have seen this in movies before. So occasionally in some action-packed adventure, maybe it's someone's trying to steal a priceless gem from a museum or from somebody's house, and they have these invisible lasers all over the room. And so they spray something, or I've seen it like where they smoked a cigarette, and then that smoke or that spray, whatever they use, started to drift across the room, and you could magically see the laser beams that would set off the security camera. That's using the Tyndall effect also. So Tyndall effect, light passes through a solution unaltered, but it's scattered in a colloid. So it's a fun lab to do. If you're on campus, I'd let you do that one. The last part of this little subsection part is going to talk about dissolved gases. So with dissolved gases, we have some special, unique things that we have to think about. One of the things deals with something called Henry's Law. Now, Henry's Law was named for a guy, William Henry, who was an English scientist back in 1775. Okay, now think about that just a minute. In 1776, the U.S. declared independence from Britain. This is the year before that. So think about the technology available. Well, more specifically, the lack of technology available. So a lot of their instrumentation was really crude at this point in time. So it's amazing the scientific advances that they came up with. Anyway, on to to continue on with our subject. Henry's Law deals with the solubility of a gas, and it deals with pressure. It says that you have increased solubility with increased pressure. So this is the reason why pop will go flat once you open it. So normally whenever you get a soft drink, it's been bottled under really high pressure, up to like 10 atmospheres, I've heard. And then when you get that bottle of pop and you open it, what's the first thing that you hear? Yeah, it goes psh. And then all the little carbon dioxide that had been dissolved in the water starts to want to come out of the water. Now, hopefully you didn't shake it or else it's going to explode. But the idea here is that we're decreasing the pressure above it, and so it decreases the solubility. That's Henry's law. That's one thing to think about. Another thing to think about is dealing with temperature and solubility. Now, gases are different than solids. With a gas, as you decrease the temperature, you increase the solubility. So this means that hot pop will go flat faster. Your cold pop should hold on to the carbonation a little longer. Well, at least that's the idea. The very last thing on here talks about nucleation. Nucleation is a process which initiates the formation of a distinct state of matter within a solution. So probably the most famous example of nucleation is the Diet Coke and Mentos, which is over there on the right-hand side, where you'll open up a bottle of Diet Coke and you drop in Mentos, and then all of a sudden it just like spurts out like crazy. Well, any type of pop will work. They like to use Diet Coke because it doesn't have sugar, so it's easier to clean up. And Mentos seems to be the very best candy to do this. And they're trying to come up with a full explanation, and no one has a really, really good explanation why. So they like to say it's because of the nucleation sites. Now, you can do this on a much smaller scale with a glass of soda, or if you're of legal age, a carbonated alcoholic beverage. I'll leave it at that. And if you sprinkle a little bit of salt or a little bit of sugar on top, you'll actually cause bubbles to start to form. It just allows a place for those bubbles to start forming. So that's nucleation sites. So Henry's law is actually applicable to our everyday life. It deals with the carbon dioxide and oxygen in your blood. And so your book goes through a couple of examples of that. It talks about the blood alcohol using a breathalyzer. Have you ever wondered about that? They say that they're gonna test your blood alcohol limit, but they don't take your blood, they have you breathe into something. Well, that's because of this solubility of the ethanol molecules into your blood versus what likes to be above your blood. Yeah. Another example is acid rain, where we can look at the amount of acid that goes into rain, your nitric acid and your sulfuric acid. So if you want more information, go back to your textbook and look. I'm just more interested that you're familiar that there are some examples of that Henry's law.